Hi everybody, this is a draft recording, a first draft recording of the following talk. The $1 million puzzle, Hadrons and Quantum Computers, Why Modern Physics Needs a New Global Mathematics. So let's see if we can change pages here. Alright. So, the standard model of particle physics, the theory we have for describing the microscopic world, says that besides electrons, I'm simplifying somewhat clearly, matter is made of quarks. You've seen this picture before, let me recall it. So the idea is as you zoom in ever closer into the structures of matter, say starting from a crystal lattice, you see atoms. The atoms have nuclei. If you zoom in closer, you see the nuclei consists of protons and neutrons. And if you zoom in yet closer, the idea is that you might see that a proton consists of quarks. These are meant to be elementary particles, three of which constitute a proton. In general, there's hadrons, like the proton, the neutron is also a hadron, that are thought to be bound quarks in this way, that consists of bound states, or that are bound states of quarks. That's the standard model of particle physics, or one aspect of it. Now, popularizers say that the standard model is so good as a physical theory that it leaves no room for improvement. So an early verbalization of this is by Voigt, 2006. The standard model is just too good. This is echoed later by Dosch in a review on QCD, where he says many physicists complain that the standard model is too good. And it keeps going this way. Recently there's this Big Think review by Ethan Siegel. As of 2025, the standard model still hasn't cracked. So the attitude here is that for theorists it's a frustrating situation in that the theory cannot be improved, allegedly. Experiment just keeps confirming this old, now fairly old theory. In particular, they say that experiments fail to find particles that are not already predicted by the standard model. Here's again some examples from web pages. Sorry folks, the LHC didn't find a new particle after all, in Wired at some point ago. And here more recently, 10 years after finding the Higgs, which is the one fundamental particle that the LHC, the Large Hadron Collider, the big accelerator experiment that is currently running and has been running for years, the one particle that it found. And 10 years after the Higgs was found, physicists face what they call the nightmare scenario of finding nothing else. Nothing new has been found. Even the Higgs was fairly securely predicted. It's regarded as a confirmation of the standard model rather than an extension of it. It's regarded as the final building block that confirms it all. And so the attitude here is nothing else has been found. We just know too much. We're so frustratingly good informed about the physical world that there's nothing left to figure out, it seems. That's the claim here. And yet, if you actually go to the LHC webpage, you will see that experiments find unpredicted hadrons all the time. So this is a page made by Patrick Koppenburg, who has a whole web page on this. I extracted this one plot here. It shows that on average, roughly 5 new hadrons are experimentally found every year. Have been since 2012. You see this. So on the vertical axis here, we see the number of hadrons, the total number of hadrons that have been found, new hadrons that have been found by the experiments, and on the horizontal axis we see that the years pass by. So you see it's almost linearly increasing with time. They keep finding and finding new hadrons. And as Patrick Koppenburg continues in the article that this is taken from to highlight, is that even though there are some predictions for some of these particles using some methods, we come back to this in a moment, there is by and large actually no theory that would predict these hadrons, these resonances. And somewhat politely, Koppenburg says experimental guidance is needed, which is a polite form of saying that theory is not in place. We don't actually know what's going on. We will actually just have to measure things to figure out. You cannot go to the standard model of particles and ask what is the next particle we will find here. Moreover, even if you're not directly interested in the hadrons themselves, but just in other processes that just involving electrons or muons, say, then even then the hadronic properties and the lack of their understanding is known to mess up predictions of the standard model in other areas. So this is here something called flavor anomalies. There's hadronic uncertainties here, and this article highlights that what's called hadronic form factors remain one of the primary source of uncertainty for understanding these flavor processes, as they're called. Some non-hadronic processes where in what's called loops the hadrons do contribute. Here's an article referring to a big discussion that had been had in the last years about anomalies or not in the anomalous magnetic moment G-2 of the electron and the muon, and tensions remain. Hadronic vacuum polarization is a source of uncertainty. So even though this is an experiment purely concerned with electrons and or muons, where no hadrons explicitly appear, since they always, in the standard model, everything kind of can interact with everything else if it's physically allowed. So in loop diagrams there may be these contributions by hadrons and they actually mess up, or they don't. Nobody really knows the predictions for these electron-muon properties. Here's another one, hadronic uncertainties versus new physics. So new physics is the term that physicists use for effects that are not actually predicted by the standard model. The theorists are eager to find new physics, to find something, as we've seen before, that is not actually yet explained by the standard model. And here they notice, well, it's actually hard to decide, because due to these hadronic uncertainties, it's not actually clear what the standard model predicts. So it's actually unclear whether something you see in experiment is new physics or is actually described by the standard model, because you don't actually know exactly what the standard model is actually predicting. So what gives? It's a curious situation. On the one hand, there's these claims that the standard model is just too good, nothing remains to be explained. And on the other hand, we've seen that even properties of ordinary matter, of hadrons, are not actually really explainable by the standard model. Well, it's a public secret that this idea of quarks is actually a peculiar theory as far as physical theories go, even so it's so well established now, it's so mainstream. But the public secret is that individual quarks actually don't exist. So we say things consist of quarks, but actually individual ones of them are not meant to exist. Only quarks bound in hadrons, mesons and baryons, are actually meant to exist. So the proton we see is meant to be a bound state of quarks, but we never see the individual quarks, just the bound state. But the way they bind is not actually explained by the theory. So that's a very curious state of affairs. The attitude in particle physics is that the standard model explains hadrons in principle. So that's the attitude you have to have in order to decide that there is no mystery left, that the standard model is just too good. You have to assume, well, in principle, it explains these 5 hadrons that are detected each year, even though they're not actually explained, but in principle they would be. So, but in practice, it barely does, to put it politely. There are various rules of thumb, effective field theories and models that are being used. They go by a bunch of names. I'll just mention them just to show how many there are. Current perturbation theory, this is in no particular order. Constituent quark model, Nambu-Ionah-Lazinino model, heavy quark effective theory, Skirm model, QCD sum rule, bag models, more recently holographic QCD, we'll come back to that, and so forth. So all these are models that try to explain certain aspects of hydrodynamics in lack of an actual fundamental theory, which the standard model is meant to be. So you see, this is not entirely unlike alchemy, where we don't really understand what's going on, where we pretend and make up ad hoc explanations as we go along. Why is the situation in such a bad shape? Well, the elephant in the room is that hadrons are known to be non-perturbative effects. So that means they're not just small perturbations of the vacuum. Here's an illustration of what this means. Imagine the vacuum of the universe. Empty space is like a rope. Then a small perturbation of that rope could be like a little wave traveling along that rope, as shown in the top part of the picture here. You just shake the rope a little and a wave will propagate along it. That is a state, an excitation, that is a small excitation of the vacuum in this picture. But it is known that hadrons are not this form. Hadrons are more like, of course this is a bit of an analogy, but it's actually made quite precise by, for instance, the Skirm model that we've just seen before. Hadrons are like knots in this rope. So if you have a knot in this rope, is something you cannot actually reach from the stretched rope without untying the rope, knotting it and tying it back. So this is a state of the rope, if you will, which is not a small perturbation of its evenly stretched form. And it's known that hadrons are such non-perturbative excitations of the vacuum. And now, the quantum field theory that we usually mean when we say quantum field theory is that which has been developed in the 20th century, and that was predominantly, if not exclusively, perturbative. So all the tools we have when we talk about quantum field theory these days still really refer to perturbation theory. So the tools we have really only describe the top part of the picture. They do not apply to the bottom part, which however is where the hadrons live. So that's where this problem arises, that we have a theory which really can only compute in this situation. We know we would have to compute it in this situation, and we can't. And so we say, well, okay, but if we could, then we would. Just to amplify how little it is that we actually understand when we say we only understand perturbative phenomena. So perturbation theory really means, in a slightly more technical sense, that we're doing infinitesimal perturbations in what's called the coupling constant and Planck's constant. So in the strength of the interaction of particles and in their quantumness, in this property that describes microscopic particles, this special new property they have. Perturbation theory means that we really consider only an infinitesimal neighborhood of zero in these two constants, coupling constant and Planck's constant. So this little blob here, which I call perturbation theory, around the free and classical theories, you should really envision this as being an infinitesimally thickened point. It's as tiny as it gets. And the whole plane here illustrates the entire space of quantum field theory, which can be a huge space. It's mostly unexplored. All this region is unexplored because all of it is non-perturbative. So the non-perturbative regime is huge. What we currently understand with 20th century physics is just this tiny infinitesimal neighborhood of zero here. So that is the big problem of 21st century physics, that it really doesn't know about most of the space of quantum field theories. The theory space, I mean, here. So this has been realized, this problem, of course, for some people who care about precision. And mathematicians have actually declared it to be one of this millennium's problems, one of the millennium problems in mathematics. The Clay Math Institute has declared a bunch of them, famously, and one of them is called the Young-Mills mass gap problem. That is essentially the question how to make theoretical sense, actual theoretical sense, not with some ad hoc rules of thumb, but actual fundamental theory-wise, of the problem of confinement of quarks into hadrons. Now, there's a technical caveat here, which is not important for the level of precision of this talk. The Clay Math Institute is actually asking for the mass gap in pure Young-Mills, which doesn't have hadrons, it has just glue balls, but it's precisely the same question, the same kind of phenomenon. And it's just the easier part. The Clay Math Institute is calling a millennium problem actually just an easier version even of the actual problem of hadrons, just the glue ball spectrum. From this perspective, the question for the full understanding of hadrons is actually even more of a millennium problem. And so, famously, the Clay Math Institute offers $1 million prize money for anybody who solves this problem, which, of course, the solution of this problem is not maybe measurable in dollars, but it gives you an idea of what scale of problem this is. So that is the situation in high energy physics. Now, analogous issues actually haunt condensed matter theory. So in condensed matter theory, one doesn't care primarily or not at all about fundamental particles, but about situations where many ordinary particles condense, as one says, to solids or fluids. So this describes the actual world we see and touch each day around us. Metals, fluids. Here, non-perturbative strong interactions are referred to mostly as strong correlations. So that's just a slightly different use of terminology for what's essentially the same fundamental physical issue. So to illustrate this, here on the left, you see weakly coupled electrons. So electrons, they are electrically charged, of course, So they interact with a Coulomb force. They repel each other by electrostatics. But it's a surprisingly good approximation for many materials, such as ordinary metals, for instance, to treat the electrons as if they were free on some background, and as if they were not interacting. Of course they are interacting, but it's a surprisingly good approximation to behave as if the coupling to each other is small, so as to behave as if we're in this perturbative regime. And many of the successes of 20th century solid-state physics come from this assumption. There's the Fermi liquid theory, which famously explains a whole lot of aspects of metals, for instance, by this picture of weakly coupled electrons. But that is not the full story. Electrons, you can push them into states, we'll see examples of this in just a second, where they are strongly coupled. So this picture here on the right indicates that as the coupling, interaction of these electrons becomes strong, when one moves, then everybody else has to adjust its position accordingly because they're also strongly coupled. So now the whole bunch of electrons acts like a funny new liquid or gas or fluid that has or can have remarkably new properties. These are called strongly coupled electrons. Yeah, they show remarkable but still largely mysterious behavior. Mysterious for essentially the same reason as hadrons in fundamental particle physics are mysterious, because they are strongly coupled systems. So here's an article which highlights the strong correlation puzzle, which you can find somewhere on the web. And it's interesting that, so this article came out claiming, as you can see here, claiming a solution to one of the most famous problems in theoretical physics, namely, concretely they refer to solutions of the Hubbard model, which is a model for electrons that, theoretical model, a rule of thumb for how to describe electrons, which in principle reaches into the strongly correlated regime. But they then highlight the solution that they're actually advertising in this article is an experimental one. It does not rely on theory. So these authors highlight that there is actually no good theory for strongly coupled electrons. Well, there's lots of theory around it, just about all these rules of thumb that we just saw, these effective theories for hadrons. So there's lots of Ansätze and ideas for how to model aspects, and people certainly understand stuff. There's no good fundamental theory. For instance, quantum Hall systems, that's the ones we'll be focusing on here. These are essentially two-dimensional electron liquids in a transverse magnetic field. So here's a cartoon of the picture. You somehow confine electrons, shown as little balls here in this picture, to an essentially two-dimensional surface, usually an interface between two semiconductor phases. And then you have a magnetic field indicated by these arrows here going transversely to that plane. Indicated here is how the electrons interact with each other with this Coulomb force that we saw before. So potentially forming a strongly correlated system. So this is the general setup of quantum Hall systems. And something remarkable happens when there are exactly an integer number k, say, of magnetic field lines per electron. So I'll try to indicate this in this picture here, where you have, on average, 3 of these arrows, so 3 flux quanta, as we will say, of the magnetic field associated with each electron. One says that, one calls this a fractional quantum Hall state, at filling fraction 1 over k. Nu, it's 1 over k, meaning there's 1 over k of an electron associated with each flux line, of each flux quantum. So, on such a backdrop, on such a fractional quantum Hall backdrop, which turns out to form one of these strongly correlated, very interestingly behavingly states of electrons, on such a backdrop, every further surplus flux quantum above the state of exact filling fraction, every surplus flux quantum indicated in red here, is correspondingly like the lack of 1/k of an electron, right? Because on the backdrop here in this new kind of strongly correlated vacuum or reference state, every flux quantum is associated with 1/k of an electron. So if you have an unpaired flux quantum, it's like a lack of 1/k of an electron. And for that reason, these unpaired flux quanta are also called quasi-holes. So solid state physicists say they have a hole if an electron is missing, where an electron could possibly go. So these quasi-holes appear like fractional quasi-particles in the fractional quantum Hall liquid. So let's change the picture here. I need some vertical room in order to show time evolution. I will replace now these surplus flux arrows here by the other notation for magnetic flux, by just a circle with a cross. So this circle with a cross and this circle with a cross indicates these two unpaired magnetic flux quanta. And the remaining situation we stop showing in graphics because this is now our backdrop. This is the new vacuum, the strongly correlated vacuum that we are looking at. This is our fractional quantum Hall state. So this picture is now a cartoon of two quasi-holes, two unsurplus flux quanta in a fractional quantum Hall system. And the remarkable thing is that the braiding, as one says, of the world lines of these flux quanta, these surplus flux quanta, has an amazing property. So meaning as these start to move now in the surface, so that as time progresses vertically, which is now indicated in this next picture here, so as time progresses vertically, that the world lines, the positions, so this little thread here is now meant to be the position of this flux quantum as time progresses vertically. So as these positions braid around each other, move around each other, the quantum state, and I'll say more about this in just a second, so the state of this fractional quantum Hall liquid changes. So this is usually denoted by this letter psi here, these funny angular brackets around it. It changes by a complex phase, so it changes, that's the point. And it changes in a way that depends only on the topology of this braiding process. So that is a most remarkable property that does not happen for quasi-particles in usual systems. That is a result of this strong correlation that this background vacuum fractional quantum Hall liquid here has. So these processes, this curious process here of braiding out world lines of these quasi-holes, is a way it may serve as topological quantum gates, and that's a big deal. So let's talk a bit about, I'll come back to this picture here in a moment. Let's talk a bit about what is quantum computing. So here's a crash course on quantum and quantum computing on one slide. You know everything about quantum computing after this slide here. So what is a quantum state? Well, on very small scales of angstrom, of nanometers, so nanoscopic matter changes its properties. It's no longer behaves the way we are used to in everyday physics, but it picks up what's called these quantum properties. And that means a lot of things that I cannot explain in this talk alone here, but the key point is that there's some kind of probabilistic aspect now to what the actual state of a system is. And so a quantum state is a somewhat probabilistic state of nanoscopic matter, and conventionally, since Dirac, denoted by these funny symbols, psi and these angular brackets. It's an element of some Hilbert space, so technically we're looking at this as a vector, technically in a vector space, infinite possibly dimensional vector space with an inner product. So a quantum state just means it's the state of matter at nanoscopic scales. And so then a quantum gate is a controlled transformation of quantum states. It's some operation that you do on a material, like a logic gate in a computer, that's why it's called a gate, that takes all the quantum states in one Hilbert space to those in the other, so that it takes our quantum state psi to some other state psi prime. And of course, technically these quantum gates have to be unitary operators of this Hilbert space, so they're linear maps that preserve the Hermitian inner product. But the point here is a quantum gate is just some controlled transformation of quantum states. And then it's called a quantum circuit. It's just a controlled algorithmic combination of quantum gates. So if you chain a number of such quantum gates after each other, you go from one Hilbert space to the next in a controlled fashion with operations U1, U1 prime, or U prime. Then you call it a quantum circuit. And finally, a quantum computation is a quantum circuit that is designed so that its output is some computation. So if you arrange your quantum gate such that, and I'm evidently simplifying here somewhat, such that you know it will take your input states to certain functions f of them, then if you know exactly what function your quantum circuit is implementing, well then actually implementing that quantum circuit in reality is the way to compute that function by a machine. You implement your quantum circuit on some material, on some quantum hardware. In the end, you measure your quantum state and you find the value of f. Clearly simplifying here for those who know what's actually going on. But like in an ordinary computation, right? You run a physical process that in a way computes the answer to some problem. So in the end, you measure the output of that process and you can read off the computation. So now the idea of quantum computation is to do the whole thing with these nanoscopic quantum states, right? So the picture of classical computation looks very much like this, only that all these states, instead of being vectors in some Hilbert space, are actually just elements of a finite set of configurations of bits. And the whole point of quantum is that it allows these finite elements to be somewhat more sophisticated. That makes a big difference. So it can be shown theoretically that for certain tasks, very specific tasks, so not general tasks, but for very certain specific tasks, quantum computers could be vastly more powerful than classical computers. And that theoretical result is what drives the interest in quantum computers. But again, this is actually a statement in principle. The big question is how to actually make that happen in reality. It works on paper where you can idealize, whoops, I almost dropped here, where you can assume all idealizations that you wish, but in the laboratory it is a different story. So the major hurdle for quantum computing is the decay. The technical term is decoherence of the quantum state. So quantum states are very fragile. They tend to decay. Here's a cartoon that I tried to draw with some computer help on what's going on. So the special property of quantum states, and hence of quantum computers relying on them, is that quantum states can be superposed. If you have two states, psi and phi, you can, they're technically vectors in some vector space, you can add them. So in physics translation, that means that in a state psi plus phi, the system is in a funny way both in state psi and in state phi. It is a superposition of both. You will have heard of Schrödinger's cat and these things, which is both dead and alive. That is referring to this kind of superposition. So for a quantum computer to do its quantum magic, it has to operate on such superpositions. But now all interaction with the environment, indicated by these wiggly arrows here, which might be heat, for instance, might be photons that impact on our quantum system. Every little interaction with the environment tends to do away with this decoherence, indicated here by the fact that what used to be a single kind of greenish sphere here is pushed by the environment to decompose into a blue and a yellow sphere. And as the environment pushes further, these two spheres are separated and become a classical superposition where the system is now actually just either in state psi or in state phi, in the usual sense of or. It's either in this state or in that state, where here it was in a sense that can be mathematically made precise, it was in both states at the same time. So this decay, this decoherence is what you need to avoid for harnessing the power of quantum computing. You want to be in this left realm, but all interaction, the tiniest interaction with the environment, pushes the quantum computer to this decohered realm. That is the big technical hurdle of quantum computing. So how to deal with this? Well, there's essentially two major approaches for how to actually go about realizing a working quantum computer. Currently, quantum computers exist. That's why you hear in the news about quantum computers all the time. But the public secret is they're tiny. They run for a microsecond before decohering, and they work on a couple of hundreds of qubits at best. So there's nothing interesting you can compute with the current existing quantum computer. The big question is how to use these toy machines that currently exist, how to put many of them together and have them work for more than a few milliseconds, for hours and days, in order to do useful quantum computation. And so there's two approaches. The currently dominant strategy to what's called utility scale quantum computing. It goes by the acronym NISQ and QUAC. So NISQ is for noisy intermediate quantum system. This means we're operating on a noisy system, and QUAC means quantum error correction. So the idea is we run on this shaky system while we keep correcting it. So unstable quantum memory decays in milliseconds, and the idea is to keep it alive by having a classical computer attached to it that continuously does what is called quantum error correction. It continuously tries to fix the quantum computer. And what is not often admitted, what is hard to grasp, and that's why I drew this picture of it, is that if you actually plug in the numbers of what kind of classical computer you need in order to stabilize a useful, meaningful quantum computer, you need a humongous classical supercomputer. And in fact, that's not even enough. Even the latency of signals running through cables being processed by the supercomputer and running back into the quantum computers will have time intervals that are too long for the rapid decay rates of our quantum system. So what one needs is actually, one needs to integrate, and that's meant to be indicated by this inner circle here. One will need, in order for this picture to work, one will need to develop new kinds of superconductors that can be put in a fridge, that can do their petaflop operations or high rate classical computations without producing so much heat as they usually would, that could destroy the low temperature at which the quantum computer should run. So there's a kind of extreme picture that people envision for how quantum error correction will actually end up in the end game. The idea of using NISQ plus QUAC really envisions that besides developing quantum computation, we will actually have to develop new kinds of classical supercomputers that operate under conditions that are presently actually unimaginable. So it's quite a bit of speculation engineering wise that this picture will work out. It's maybe good to visualize this in more simple forms. I suggest that you should think of quantum error correction as the attempt to continuously refill leaking buckets. So I drew this cartoon here with the help of Gemini, which illustrates what's going on. So each bucket here, the water in it is a qubit, is a bit of quantum memory. And the fact that the quantum memory keeps wanting to decay, to decohere, is illustrated by the fact that these buckets are leaky. They leak water all the time. So the strategy of quantum error correction is to add a classical machine, indicated by these cartoon machines here, classical machine to the situation, which kind of catches these errors, catches the water, and refills the buckets, so restabilizes the buckets continuously. You see, it's a hard job for these machines to keep up with all that leaking water. But when you see this picture, it's clear, from the picture it's clear that there should be, in principle, could be a more fundamental, more satisfactory solution. Just fix these darn buckets. Just plug them. What you want to be doing is get rid of these error correction machines, at least to a large extent, to some extent, and just have these buckets be stable in themselves. Why would they be leaking in the first place? So that second idea, passive stabilization, that is the idea of topological quantum computing. If you could find fundamental physical principles that would actually prevent the states, the quantum states, from decaying in the first place, then this whole problem would go away. And if that could be put into practical, implementation, we would be able to, maybe in the future, build a large-scale quantum computer. So one candidate platform for such topological stabilization are just those fractional quantum Hall liquids, those strongly correlated electron gases recalled in 2D materials, the presence of a transverse magnetic field. So now let's come back to the picture we had to illustrate why that is related to quantum computation. So on the left, concentrate on the picture on the left, we see again a cartoon of or two-dimensional liquid of electrons, and inside there we have these quasi-holes of surplus flux. And now if we could, in a controlled way, braid the world lines around each other to go from one such situation to the next one as time now flows horizontally, the quantum state of our system would change. So we would implement a quantum gate. But the whole point was, remember, that this braiding phase that operates here depends only on the number of times that these world lines braid around each other. It does not depend on how this trajectory here might wiggle, which is not really indicated in the picture. So these look like straight lines here, but in practice, of course, there will be noise in the position of these flux quanta. And that noise is exactly which usually threatens, jeopardizes the quantum state to decohere. But now, in these topological systems, they're intrinsically insensitive to this noise. And hence, if this could be implemented, it would make for a topological quantum gate that is intrinsically stabilized. So that is the big promise of, in general, topological quantum systems, strongly correlated electrons, in particular these fractional quantum Hall systems. So these abelian braiding phases they have actually been observed in experiment by different groups, which is a big deal because there are several proposals for how to realize this kind of situation. Some of these proposals exist only on paper. Others are not actually fundamental realizations but quantum simulations on non-topological systems. And then there's example of one big company which claims to have solved something like this, but nobody else can reproduce their claim. So it's a big deal that in the fractional quantum Hall systems, this actually is known to work in principle. Of course, there remain many open problems. For actual application in quantum computers, one has to know how to make these phases be non-abelian. I'll say more about this maybe in a second, and how to actually control this braiding. So there's many open problems, and many of them are related to the fact that even though we understand these strongly correlated FQH electron gases a little bit, by and large, actually there's lots that remains to be understood due to this puzzle of strong correlation. Alright, so that was the motivation part of this talk. So the question is then how to actually understand non-perturbative physical fields. So we now step back and look more at the general theory. So how to actually progress? What is it that is missing in the current picture of physics? And the answer that I'm going to present now and talk a bit about is, of course, the answer that I've been working on a bit in the last years, which is why I can talk about it. It's called flux quantization. And it's sometimes called charge quantization. And it's a term that implies or stands in for other terms that are commonly used in the context of non-perturbative effects in QCD. It relates to solitons, monopoles, skyrmions, instantons, and other such sphalerons and whatnot. Sorry. And so what I'm going to say now is a very brief toy version of what we've written a review of in this encyclopedia article here, Flux Quantization, which in turn is based on other articles and books that we've published. I'll show some of them. So if you wanna see more details for the sketch that I'm giving now, the very elementary introductory expository sketch that I'm giving now, check out this encyclopedia article. So okay, let's step back. So in 1852, Michael Faraday strewed iron filings over the poles of a magnet and saw the following. And we've seen these pictures before. This is from Faraday's diary, directly from his diary from 1852. He did the first experiment along these lines actually December 1851. So around the new year, he saw this remarkable picture. See here on the left, top left, is a rod magnet. I guess he put a sheet of paper above it and then strewed these iron filings over it, and they're arranged in these lines. So it turns out, this reveals that the magnetic field that is kind of carried by this rod magnet, or sourced by it as we say these days, travels or manifests in these what's now called fields lines. So here's a close-up picture. That's actually the one he did in December of the year before, of the tip of one of these rod magnets. You see the iron filings emanating from one pole of the rod magnet going into the other. And so the modern way of describing this is that we say, okay, let's measure the strength of the magnetic field by sort of how many flux lines, how densely the flux lines go through a given surface. So see, I indicated a yellowish little surface here, and flux lines go through it. As you make the surface larger, you see that its area becomes larger, but the number of flux lines through it remains the same. So the density of the flux lines is a measure for how strong the magnetic field is. Ooh, it's getting a bit windy. And so the modern way is to devise a mathematical machine that reflects this density. So we want a mathematical machine called F2 here, which assigns to every little piece of surface with edges delta x1 and delta x2 in this picture here, assigns the flux that goes through this little surface, so that once you know this F2, you can in principle know the flux through any big surface by subdividing into ever smaller little surfaces, applying the F2s to each of them, and then adding the whole thing up and taking the limit where the surface area goes to zero. And that is of course called the integral. So the modern terminology is that this F2 is called a differential 2 form. 2 means that refers to the two-dimensional extension of this little piece of surface here. So this is how we, in modern physical theory, one describes the electromagnetic field by a differential 2 form on space-time, which you think of as assigning to little surface elements the total flux of the field through that surface. So magnetic flux density diverges from or at the monopole and is divergence free elsewhere. So we've seen this picture before. Here's Faraday's experiment. Here's the idealized form. Suppose you have the end, so monopole of the end of a rod magnet here, the magnetic monopole, just a single of these poles. Then we saw from it field lines emanate, so they diverge from this picture in that when you have a little sphere around the pole, then whatever sphere you have, the total flux through the sphere will measure, will tell you that there must be a monopole inside because there's total flux going outside it. Whereas when you draw a sphere somewhere else with no monopole enclosed, then the total flux through the sphere will be zero because there will be as much flux coming in from one side as will be going out from the other side. So differentially, this fact that away from magnetic monopoles the flux density is once it's divergence free, is written by the symbol dF2 equals 0, the Rahm differential is 0. It's called the Gauss law. And actually magnetic versions exist of this Gauss law. That will play a role as we go along. So a little later, in 1931, Dirac, another famous physicist, noticed that there is more to this story. In this famous article, Quantum Singularities in the Electromagnetic Field. Namely, Dirac noticed that the total magnetic flux through any, well, this is in paraphrase, through any surface comes actually in discrete units, in integer multiples of flux quanta. I should say here, through any closed surface. So this is a curious global constraint. Locally, the flux density can indeed be anything, through any little piece of open surface, can be anything. But when you close the surface to a sphere or a torus or something, then actually the total flux through that closed surface must integrate to an integer multiple of some unit flux. That is, in a sense, what Dirac noticed back then, ever since we speak of Dirac charge quantization. In the 1960s, just to amplify these flux quanta, as they're now called, were actually seen, photographed with an electron microscope in certain superconducting materials called type 2 superconductors in the form of induced abrikossov vortices in the electron current. So there's actually actual photographs of this situation with an electron microscope. But here's a cartoon picture, a schematic picture. The slab here, the cuboidal slab here, is meant to be a piece of superconducting material, and again we have magnetic flux lines going vertically through it. In a type 1 superconductor, and this will play a role later, the flux lines are forced out to not go into the superconductor, whereas in a type 2 superconductor they can enter it, but only in discrete units. So they can form a discrete unit of magnetic flux, called now the flux quantum, may enter the superconductor, and it will make the electrons in the superconductor revolve around the flux line and form a vortex. It is that vortex in the electron movement that is actually seen in an experiment. But the quantization effect, the fact that there's an integer number of these vortices, all of which correspond to a unit magnetic flux, that comes from the quantization of the magnetic field. So that is an experimentally verified fact. And so now as we try to formulate what's going on here mathematically, it turns out that this shows that the magnetic field, on top of this two form that Maxwell and Faraday introduced as a description of the magnetic field, there must in addition be a classifying space, and that is what brings in the global topological non-perturbative aspect to the story. So the usual classifying space of electromagnetism, if you open a textbook, is described as a space that is known as CP infinity. Now CP infinity is hard to visualize. For this talk I want to instead give you a kind of visualization of CP2, which is still hard to visualize. It's a four-dimensional space, but I can at least show something that gets close to an actual visualization. So we're talking about classifying spaces that are not physical spaces. They're not spaces you can travel to. They're abstract mathematical spaces of all possible charge configurations in a way of a magnetic system. So CP2 is defined to be the abstract mathematical space of complex lines in C3, in the three-dimensional complex space. So we all know three-dimensional real space, and I hope you know the complex numbers. So you can envision a space that where every point is described not by a triple of real numbers, but by a triple of complex numbers. That is C3. And in there we can now look at any point and all its multiples by elements in C. This is a complex line. So a complex line is actually so C3 is actually a 6-dimensional real space, and a complex line in it is actually a surface. Well, one says it's complex line because it behaves like a real line just over the complex numbers. And due to that similarity, I can offer this cartoon picture here. Remember, we're really talking about a 4-dimensional space here, CP2, but it looks a bit like this. If the real complex real space we envision for a moment, for lack of any other visualization tools that we have, as a real space shown in this picture here, but we remember that what is actually meant as complex space, then a point in CP2 is actually a line through the origin, indicated by the dashed arrows here, a line through the origin in this space. So CP2 is the space of all these lines. And so it looks a bit like it's the complex version of the projective of the result you get by having an actual sphere and identifying opposite points. But okay, just for those who... Anyway, so this is the point, this space CP2. And an interesting fact about this topological space CP2 is that even though it's not physical space, it has a priori nothing to do with physical space. It's a very kind of exotic space as far as physical manifolds go. Of course, a very simple space as far as topological spaces go, but anyways, so it carries a flux density. There's a 2-form on this space, which has this property that Dirac demanded. It has the property that if you integrate it over any 2-sphere in CP2, the result is an integer. So there is a kind of universal avatar of the quantized flux on this space. And so the idea now is that Dirac's flux quantization says roughly that the magnetic flux fields on space-time are to be accompanied by a classifying map from space-time to this classifying space, which serves to connect to that already Dirac quantized flux density that CP2 carries. So here's the picture. So on the left we have a cartoon picture of our physical space X3 here, with one of these little surface elements in there. And we want to say what is the flux density F2 of the electromagnetic field in our physical space. And we say, well, instead of just defining any 2-form, we need to be able to pick a map. So a function that takes any point here to a point in this abstract classifying space CP2 that maps space-time onto CP2, and hence in particular maps our surface elements, 2 surface elements in CP2. And then we declare that F2 has to be such that its value on a given surface element is actually the value of that avatar flux density, little f2, lowercase f2, that exists here on CP2, evaluated on what's called the push forward, on the image of our little surface as you move it over here. So we move the surface element to there and then evaluate the avatar flux density on it and declare that this is the result, should be the result of our flux density on space-time. Mathematicians say, conversely, that we've pulled back along chi, this is the notation chi upper star, that we've pulled back the 2-form F2 from CP2 to space-time. And so Dirac flux quantization says that the flux density, the actual flux density on space-time comes from this universal flux density F2. I'm simplifying a bit here. There's some homotopies involved there, which I'll indicate in slightly more detail just a little later. But for the moment, it's just keep this in mind. So this is the modern formulation of the electromagnetic field. Flux density is F2, as Faraday and Maxwell visualized them. But then in addition, what might be called a charge classifier, a map chi, to some classifying space and some compatibility condition between them. So if you look in textbooks, they will often give you different incarnations of this triple of data that I'm stating here. Many textbooks will say the Dirac quantized electromagnetic field is a connection on a circle principal bundle, and that is equivalent to what I'm saying here. I'm stating the flux quantized electromagnetic field in a way that generalizes and is adapted, that lends itself to the generalization that we'll be interested in a moment. So the question is, what is the corresponding deformed effective description of surplus FQH flux? Right, so we've now recalled how ordinary magnetic flux is quantized. So now we want to turn to the problem of understanding the non-perturbable formulation of these strongly coupled, strongly correlated electron gases in fractional Coulomb Hall systems. And this is where I'm now giving a sketch of a theorem that we've been proving in the last years, which which shows what's going on. So for surplus FQH flux, remember these were these flux quanta, not in the ordinary vacuum of space-time, but on this backdrop of a fractional quantum Hall state. And the statement, since I've already used CP2 as a classifying space for the ordinary electromagnetic field, sounds actually rather simple, but is profound. Namely, the statement is, well, we need to probably deform the classifying space now in order to describe the effective interaction with these electrons. So these surplus flux quanta, they have some interaction with this electron gust, so they're not ordinary flux quanta anymore. They are described on this backdrop of a fractional quantum Hall system. So we're trying to ask, well, if they still have a classifying space, what might it be? And we're saying, well, it's a deformed space, it's just CP1. The picture that emerges is this, that if we now again visualize our surface or electron liquid here, it's now equipped with a map to the 2-sphere. And the way it works, what I'm describing here for experts is essentially the Pontryagin theorem. The way it turns out to work is that it will say that most of the points far away from all these flux quanta, from the anions as they're called, will go to infinity. This is actually not really shown in this picture. So envision that the far point of the 2-sphere here is called the point at infinity on the 2-sphere. And most every point of space, of our surface, goes to this point at infinity. But the vicinity, the actual locus of these flux quanta, they get mapped to wrap around this sphere. And so that's what the color here indicates. And so it's this wrapping, the fact that if you map a surface holding its boundary fixed, so all the boundary has to go to infinity here. If you wrap a surface over a sphere with the boundary fixed at infinity, it has to wrap so an integer number of times. That actually implements this flux quantization condition. But on top of just implementing just the quantization, just the fact that there's the integer number of these flux quanta, the sphere actually implements, it turns out, this is mathematical theorems that I can't really explain here, it actually implements the funny braiding statistics of these flux quanta. So it turns out that the world lines of particles that are flux quantized by CP1 this way, hence by the ordinary 2-sphere, that they actually do behave mathematically provably like the anions. So this is actually a very robust fundamental mathematical derivation or rederivation and explanation of what's happening in fractional quantum Hall systems. So this is a result of a couple of articles we wrote. Here's one you can find non-Lagrangian constructor of anions via flux quantization and cohomotropy. And then we have this argument with our colleague here, Sarah Kalel, high-dimensional anions via high cohomotropy, which rederives this theorem and generalizes to higher dimensions. And so what actually happens is that the anionic quantum states form what's called local systems of Hilbert spaces over the mapping space, over the space of all maps to the 2-sphere. So what is a local system? So this is a bit of a side issue here maybe, which I should be quick about. So if you have some space, indicated some manifold, indicated below here, then a local system of vector space means over each point in the space, you have a vector space, which we think of as a Hilbert space of quantum states, hx here over x, hy over hy. And a local system means that to each path, in the base space, there's a corresponding transformation of quantum states and a unitary linear map that takes the Hilbert spaces over the endpoints to each other. So that, for instance, if you go in a circle, as indicated here, so you go in a circle, you get an endo transformation of your Hilbert space. So these unitary operators are called the parallel transport of state vectors, quantum state vectors, along the path. And if you go in a circle, it's sometimes called a monodromy or holonomy. And the statement is, part of the theorem that I just flashed, is that this is the situation for the quantum state that we are facing with this flux quantized description of FQH systems. If we identify this base manifold with a mapping space of maps from the surface that our electron gas inhabits to CP1. So besides rigorously rederiving the solitonic fractional quantum Hall anions laws, besides rederiving the effects that have been actually seen in experiment, this new description of fractional quantum Hall systems actually predicts non-abelian anions. Remember, this was one of the open questions for how to go about using the FQH systems in actual real-world quantum computers. So it predicts that non-abelian anions should be attached to superconducting islands in fractional quantum Hall liquids. Just make a cartoon here. So if we can dope our semiconductor such that a part of it becomes type 1 superconducting so that it expels the magnetic field, this becomes a location in the surface where no onions can go, because remember our onions were really just surplus magnetic flux quanta, but magnetic flux is expelled from this superconducting island. And the theory predicts, that's all I'm going to say about it here, that there's in some sense non-abelian anionic quantum states associated with these islands, which is interesting because super semiconducting heterostructures have long been tried as a substrate for topological quantum states, but in one-dimensional systems. And the experimental claims for detection in 1D systems has been dubious. There have been retractions of articles, and people are doubting that those who still claim that they've seen the system actually did. And here it's interesting that there's an actual solid theory that says that in similar super semiconducting systems, but in 2D, this should actually work. So this theorem that there's these non-abelian onions here, this and more is described in this article, fractional quantum Hall onions, where the algebraic topology of exotic flux quanta. Oh, okay, let's get back to this fact that we chose a different classifying space. We changed the classifying space CP2 or CP infinity of ordinary electromagnetism to CP1. But that also means that the Gauss law is actually deformed. So it turns out, right, previously I said we're pulling back this 2 form, little lowercase f2 from CP2, and in three-dimensional space that just says that, well, okay, its pullback will also just be a closed form. Turns out when you map to CP1, there's some unstable effects that kick in, even for low dimensional, like 4-dimensional space times x. There's still a closed 2 form here, but in addition, there's actually its Hodge dual. There's a 3 form, higher dimensional, so a machine that sends 3-dimensional little volume elements to numbers, and it's no longer divergence free in the sense that its Ram differential is actually it's called the wedge product of the 2 forms. So there's some nonlinear coupling here between different fluxes, and that means the Gauss law is deformed. And it turns out that this Gauss law, this new deformed Gauss law, is actually the one of a higher dimensional field theory that is called 5-dimensional Maxwell-Chern-Simons theory. And so what is really happening here is actually that there's some text missing here. What's going on? There's some text missing. It says, so what's really going on here is that we discover that this flux quantization that we invoke by turning to CP1 is really that of a 5-dimensional field theory. And one can work out, and it's known that this 5-dimensional theory has what's called a dimensional reduction to 3D, under which it actually reproduces the 3-dimensional Simons theory that is usually used as the effective theory for these fractional quantum Hall onions. So in fact, that is the correct theory to use even on traditional grounds in order to describe the correct effective field theory for these fractional quantum Hall onions. And so we find that considering that, flux quantizing it and taking the dimensional reduction, correct theory. Alright, so there was the system for the situation for FQHCs. So generally actually higher fields in higher dimensions have graded polynomial Gauss law. So we just saw that changing the classifying space to CP1 introduces this polynomial Gauss law. This is actually the generic situation. If you look at what's called high gauge theories, higher field theories, higher dimensional, high degree flux densities in higher dimensions. They have a bunch of flux densities of various degrees, so they are machines that eat volumes, hypervolumes of arbitrary dimension. And the Gauss laws are such that the divergence of these things are expressed as polynomials in the other flux densities. So such Gauss laws equivalently characterize, it turns out, closed differential forms with coefficients in characteristic infinity Lie algebra Mathfrak A. So this is a lot of jargon here, but this is not too important for the level of detail that we're discussing here. The point is just this kind of data that encodes Gauss laws and generalized theories is all encoded in an algebraic object called an L-infinity algebra, which I'm just going to call little a here, fraktur A. And the interesting point is that another source of such data are spaces, classifying spaces, the way we've already seen. So technically by classifying space here, for those For those who know, I mean now a nilpotent space of rational finite type. But if you have a space that is a candidate space for classifying charges of a higher dimensional field theory, there's an operation on it called its rationalization. It's the topic of rational homotopy theory. It's kind of the approximation of the non-torsion aspect of this space. And anyway, there's a natural transformation that turns spaces into these data Fraktur A, called the Whitehead L infinity algebras. And as we now regard this space as being a classifying space for charges, so that we look at the maps, the space of maps from X to it, this rationalization map becomes what's called the character map that takes such maps to the kind of differential form data that we just saw before, is the differential form data that characterizes our higher flux density subject to these Gauss laws. So what I'm trying to say here is that the local description of high dimensional high gauge fields by these flux densities actually always be understood as being the shadow of charges of correspondingly flux quantized charges with a classifying space. And so that means that the global completion of a higher field theory by flux quantization is a choice of such an A. So there's in general infinitely many different classifying spaces A with the same local data, Fraktur A. So choosing one of these allows you to play the same game that Dirac did with the electric field. You can say, well, the full field content is not just the flux densities, but in addition a map to this classifying space such that the flux densities are recovered as the character map, the character image of that map. And so in order to say this, you need to make a choice for this space A, and that is the choice of flux quantization, hence of global completion, of non-perturbative at the classical level at this point, completion of the higher field theory. So this is what we describe in this book, the character map in non-abelian cohomology, for those who want to see the details. Alright, so to conclude so far on fractional quantum Hall and to give an outlook on this millennium problem, so let's first look at the left-hand side. And in conclusion, we've seen that the effective FQH fields, so these surplus flux quanta exhibiting these funny anionic braiding phases, can be realized as the dimensional reduction of a high-dimensional, five-dimensional Maxwell-Chern-Simons theory, and that admits a global completion by flux quantization by choice of classifying space, and particularly by the choice of CP1 being the two-sphere, and that choice then gives you a fully mathematically well-defined non-perturbative quantum theory of the topological sector of Maxwell-Chern-Simons theory, describing in fine detail what is observed and what is expected, and a bit more even for anyons and fractional quantum Hall systems. So the upshot here is this is a good theory of this comparatively very simple toy example of fractional quantum Hall systems. And now, of course, I don't claim that I have any solution or even a little bit of a solution to this full millennium problem, but it's just curious to note that, of course, these steps here, these two steps that we applied to the fractional quantum Hall systems, they have evident analogs for QCD, for the theory that describes quarks. So it is well known that the standard model theory, or QCD, the sector of it, QCD as it's called, that describes hadrons, or doesn't, that should describe hadrons, is also the dimensional reduction of a certain high-dimensional theory called the M5 brane theory in the Witten-Sakai-Sugimoto model. So there's an analog of this five-dimensional Maxwell-Chern-Simons theory that serves as a kind of theoretical stand-in for the actual theory you want to describe by giving it a new dress in a way, a new perspective that lends itself better to analysis. Well, and then if we, of course this isn't clear, nothing on this side is clear, that is why there's all these question marks. If we assume that this is actually the right approach to non-perturbative QCD, then the question is, well, how do you flux quantize this? And it turns out that actually has a good answer. And this is really what got me into this whole subject here. So with Hisham Sati and originally with Domenico Fiorenza, we have worked on this question of what is the global completion really of these M5 branes in what's called M-theoretic backgrounds. It turns out it also has an answer that is kind of analogous to the answer on this side. There's a helicopter above us which makes some noise. Let's wait until it's gone. Some prints going from here to there. So there's a good description, turns out, of the flux quantization of these M5 models in some version of 4-twisted 3 cohomotopy. We call the hypothesis that this is the right choice of flux quantization for such purposes, hypothesis H, because it describes stuff in cohomotopy. So this is the result of a series of articles starting with this one, twisted cohomotopy plus M-theory anomaly cancellation. And so that's all I'm going to say about this. I'm not going to claim $1 million anytime soon, but I'm just saying that there's clearly some kind of insight that is being gained here. It looks. Alright, next to look more at the mathematical framework. So that is the kind of physical approach that one can consider, that looks promising. Now let's look a bit about what so what does it take to describe this mathematically? So we need to describe what's called the non-perturbative phase space. We've seen that physical fields are encoded in triples of data. So locally there's a flux density satisfying Gauss laws, fracture A, indicated on the left here. Flux densities, and this was just notation here for these differential forms that are controlled by Gauss laws, by fracture A. And then globally, the fields are controlled by charges within a classifying space A. So there's charges here being maps from space-time to the classifying space. So the non-perturbative field content must combine these, right? We should think about, I left this a bit vague in the previous exposition. We should say, what exactly does it mean now to say a field content, field configuration is a combination of a flux entity and such a map? They live in completely different worlds. This is a differential form on a manifold. This is a homotopy type. So mathematically they live in completely different universes a priori. And yet we want to say, and this turns out to be really, I haven't really explained this, but this turns out where the gauge potentials come in, we want to say that in some sense these two objects should actually be the same, right? We saw that this F should really be the pullback of some universal form of this chi for some small values of is, with some homotopies in there. And so the global field, the actual full field content, should be some combination of this. You somehow want to make sense of such a combination where you say global fields are such Fs and such chi's connected by some A. Now, it turns out this unification exists, and only exists, in a novel universe of mathematics which unifies these two distinct universes here, differential geometry and homotopy theory. Namely, it realizes what's called technically a homotopy pullback. There's a square. You can compare this here using this character map we discussed and some deformation map which I haven't discussed. You can actually make this exist in what is called a higher geometric topos, a higher topos. A universe of math where both these extremes actually exist, where you can put them together in this diagram. And then this diagram, for those who actually know, if you demand it to be a pullback diagram, gives you actually the full definition of the full non-perturbative field theory stack, as one says. So this is again a result of this book we wrote, the character map. And here's a cartoon picture of what this high topos theory is. So it's the unification really of geometry and homotopy theory. It's the unification of this local aspect of where you talk about infinitesimal little pieces of surfaces and values in them, and this global aspect, which is the non-perturbative aspect, where you talk about how spheres wrap around each other and stuff. That is the homotopy theory. And high topos theory is the place where this unifies, where you have geometric objects that at the same time are what is called infinity groupoids. They have all this higher homotopical structure. So we're now to formulate non-perturbative physics in higher topoi. I'm just flashing some articles here that I wrote where you can find me talking about how this works. There's an encyclopedia article, high topos theory in physics, also where it's currently in print with Hisham. Geometric orbifold cohomology is very much about that topic, how to formulate Riemannian and Cartesian geometry in these higher toposes. So this can be done. And an interesting aspect here is, while these higher topoi have a reputation of being very involved, it is really more a property of their set theoretic models that is involved, or very rich in phenomena, one should say. Well, the abstract language of higher topoi themselves is so neat that it even exists actually at a computer language called HOTT, homotopy type theory. So here's a very brief sketch of how this works. On the left we see homotopy theory, on the right is this computer language that has since 10 years now or so been developed. Since 2013, I guess, 13 years now. So in this language, remarkably, the spaces of homotopy theory, the homotopy types really, are the data types, the very data types in the sense of data types that you know from your own programming experience in this hot language. The mapping spaces that we use to express the charges are just the function types. So if you just declare something is a data type of a function from here to there, that actually makes it a point in a mapping space in this language. And then the local systems that we saw encode the actual quantum aspect for these non-perturbative fields. They actually correspond in this hot language to what they call dependent types. So it's rather remarkable that they have, in this language there exists native language constructs for these rather esoteric seeming concepts that we needed, like local systems. And finally, that parallel transport that we needed to find the actual unitary operations on our quantum states are also represented natively in this HOTT language as the type transport. So these reflects exactly the structures that showed up above. And we've explored this a bit in this article on topological quantum gates in HOTT, where we describe, using this dictionary, and some refinements of it of course, how to describe in fine detail topological quantum gates in this computer language. Alright, so summary and outlook. So the grand physics problem of the 21st century is understanding non-perturbative global fields. The first main open problem is confined hardware dynamics. Unknown hadronic contributions infect all standard model processes. And as long as we don't really understand this, we should not really claim that there's nothing left to be understood with the standard model. Analogous to this, actually, even though in a very different regime, is open problem 2, the strongly correlated electrons. Here again, it's a big open question for how really deal with them, and this is needed for getting good control of a topological order, as it's called, for these topological effects, which may be needed for meaningful large-scale quantum computing. Now, there's a attack strategy that I've indicated here is first to embed effective descriptions of these fields into higher-dimensional, higher field theories. This is needed for properly dealing with strong coupling limits, not by actually running a parameter of the in theory space, but just a volume on the space-time, so just a physical parameter. And there was the crucial step, to globally complete these theories by proper flux quantization, by choosing this classifying space that is compatible with the Gauss laws and imposes the actual global description of the fields. That was the key aspect. That is where the non-perturbative information comes in, and that's where the new global topology comes in. So this is the necessary mathematical framework for this geometric homotopy theory, also known as Hadrons theory, which is a new form of global mathematics for non-perturbative physics. So global mathematics in the sense of global analysis. It is really a globalization in much the same way as we're looking for when we talk about non-perturbative effects. So these topoi are rich in phenomena, but extremely neat in the abstract. They have a computer language actually to reason about them, HOTT. So this is possibly the 21st century math that is needed for solving the 21st century physics problems. That's what I have to say here. This was just the first draft. I'll send another one later. Thanks. So how do I stop this? Bye bye everybody.